In today's sequence, we are going to study sinusoidal steady state analysis. In doing so, I am going to do something rather strange. So I'm going to start by trying to scale up this mountain the expected way. However, we're going to hit our head on a rock here, and this path is going to be really hard. So I'm going to give up. I'm going to give up halfway through and then look for an alternative solution. And we're going to find that there is a sneaky approach, that will work much more easily. So the reading for this section is 13.1 of the textbook, and hopefully you will see the relationship to this little cartoon on this front page and the content in this sequence. Let me start with a quick review. So in the past couple of sequences, we looked at second order circuits, both undamped and damped. As a motivating example, we used this inverter pair, and we said that any loop can be modeled as a little inductor, and I stuck that little inductor here in the circuit. And what that did was, when combined with the resistor and the gate capacitance of the MOSFET, it resulted in some rather strange behavior. We expected output that looked like this, a nice little step here, but in reality we saw a very funky waveform which showed some ringing behavior. And hopefully the discussion we had so far convinced you that the ringing is indeed due to this RLC circuit that is formed by the pull-up resistor, the inductor L, and the capacitance C. Alright, today we shall look at a slightly different way of looking at these networks. We are going to look today at the response of networks to sinusoidal drive. In the past, we talked about network behavior for impulses. We looked at step responses, and we looked at the behavior of networks without any inputs. Today, we are going to look at the response of networks to sinusoidal drives. So, why care about sinusoids? Why do we care about sinusoidal drives? Well, the sinusoids are an extremely important class of signal. And one of the most important reasons why we care about sinusoids is that, believe it or not, but signals can be represented as sums of sinusoids. So for example, if I have a sinusoid here, of course I can, this is the sinusoid on the right hand side. I have this could be a voltage as a function of time, and it's a sinusoid. But let's say I take the same sinusoid, take the same sinusoid down here, and then I add to it a sinusoid of a higher frequency. In this case, notice that the sinusoid I'm adding in has a frequency that is 3 times the base frequency. And then let me add another sinusoid with an even higher frequency. And what you will get, let me go and add one more sinusoid with an even higher frequency. So I'm going to add up, straight addition of the blue, the red, the green, and the yellow sinusoid. Notice that the sinusoids of higher frequency have slightly lower amplitudes, but I'm going to add up all these sinusoids, and when you add them up, what do you expect the output is going to look like? You would think that it's going to look like some garbled mess. However, believe it or not, when I add these up, the output is going to look like this. And in fact, if I add up some more higher frequency components, the higher frequency than the yellow sinusoid I have here, I am going to end up with something that looks more or less like a square wave, like so. Believe it or not. So in 6002X, I am not going to show you the theoretical foundations of why this is so, but trust me when I say that when I have a waveform, a repeating waveform like a square wave or a triangular wave, or for that matter, if I have some music signal, if I have some music signal and so on, I can represent any signal, as a sum of sinusoids. This technique that can transform any waveform into a sum of sinusoids representation is called Fourier analysis. So Fourier analysis is a technique whereby I can decompose any waveform into its component sinusoids. And in fact, for a repetitive pattern like a square wave or a triangular wave, Fourier series analysis can show that it can be represented as a sum of sinusoids. And the sum of the 4 sinusoids I showed you here give you more or less a square wave on the right hand side. So why do we care? So the reason this is really cool is that if I can now understand the behavior of circuits to sinusoids, okay, to a sinusoid of some frequency, then I can divine the behavior of that same circuit to virtually any other signal simply by representing that signal as a sum of sinusoids. Of course, my circuit has to be linear, and recall, for a linear circuit, if I take a sum of a set of inputs, then my output will be the sum of the corresponding set of outputs. So therefore, if I want to figure out the response of my circuit to a square wave, then if I know the behavior of my circuit to a sine wave of a given frequency, then I can compute the behavior of the circuit to the square wave by simply adding up the responses of that same circuit to all of these sinusoids. Okay, that is absolutely remarkable. Okay, so what that means is that if I study the behavior of a circuit to a given sinusoid, then I can then predict the behavior of the circuit to virtually arbitrary sets of inputs, provided of course that system is linear. Okay, so just to recap very quickly, sinusoids are extremely important because signals can be represented as a sum of sinusoids. So in this next sequence, we will study the response of circuits to sinusoids of various frequencies. The response of circuits to sinusoids as a function of frequency is called the frequency response of the circuit. In other words, how does the circuit behave as the frequency of the sinusoid is changed? Again, that will tell us a lot about the system, simply because any signal can then be represented as a sum of sinusoids. All right, you will see how you can mathematically break up a signal into a sum of sines for a repeating signal, or to other forms of sinusoids for non-repeating signals and so on. And you will see this in various future courses, but for now simply assume that that is true. All right, so why are we interested in studying the behavior of circuits to sinusoids? I input a sinusoid, I expect a sinusoid at the output. What's the big deal? Well, I'm going to show you a little demo that show you that this is indeed a big deal. Okay, I'm going to show you some behavior that you will be completely unprepared for. So consider this circuit. Okay, this is your good old amplifier. Okay, the MOSFET amplifier with the resistance RL, and I apply some input VC to the MOSFET. Notice here that the actual input that I care about is VI. Okay, and let's say that is some sinusoidal input, like so. This is my time axis. And I've done all the usual stuff. Okay, all the usual small signal stuff. Okay, let's say VI is a small signal. Let us say that I've biased it using V bias so that the amplifier is behaving in a more or less linear fashion. In addition, what I do is I've drawn here CGS, the capacitance of the gate of the MOSFET. I've also indicated a resistance R here, and this resistance could be the resistance of the wire that connects the source to the amplifier. It could also be the resistance of the source, and so on and so forth. But fundamentally, I have some resistance and I have some capacitance, and the output VC is taken at this point. So I apply VC to my circuit and I get some response V0. Okay, so I'm going to show you what the response V0 looks like for an input VI. And what I'll do is I'm going to change the frequency. Okay, I'm going to change the frequency F. I'm going to vary the frequency F, and then you're going to observe what V0 looks like. Okay, you will see some very, very interesting behavior as I change the frequency of VI in this little circuit. To give you a quick preview of what you're going to see, you will notice that VO, the amplitude of the output, will change as the frequency of the input changes. In fact, what you will see is that the output V0 the amplitude of the output V0 will decrease as the input frequency changes, as the input frequency increases. Okay, so the higher the frequency of the input, okay, so if I plot frequency on the x-axis, and if I plot the amplitude of V0 on the y-axis, then I'm going to show you in this little demo that the output V0 is going to change as the amplitude of V0 is going to decrease as the frequency increases. Not only that, what you will also observe is that the phase, okay, of V0 will also change. In other words, so let's say, for example, you expect that V0 will look like this. Okay, so given an input Vi, I expect V0 to look like this. But what you will observe is that as I change the frequency, the phase of V0 is also going to change. In other words, what does it mean for the phase to change? Well, V0 may be shifted to the right as the input changes in frequency. So for example, a V0 might end up looking something like this, okay, where the phase has changed. So this is going to be very interesting, and let's take a quick look. What you've learned in 6002X so far has simply not prepared you for understanding the behavior of sinusoids as a function of frequency. Okay, so hopefully this demo will motivate why we need to study this. So as another motivating fact, let's say I build this amplifier. Okay, I build this amplifier with a given gain. Okay, I've done all the usual tricks, GMRL and all of the stuff we talked about a few weeks ago. However, I'm just showing you now that my gain is going to change its frequency. Okay, my amplification is going to change with frequency. So clearly there's something else funky that is going on, and we need to understand what that is. All right, so let's dive into this demo, take a look at it, and then let's go and study the response of such circuits to sinusoids.